My name is Nick Denegre, CEO, American Perovskites, end-to-end material supply company for perovskite solar cells and optoelectronic devices. We're on a mission to really accelerate the commercialization of this technology. Uh, as many are maybe aware, there's just quite a bit of um, hype around this technology. We just heard, 97% power conversion efficiency over 6,000 hours, can be extrapolated to a 20-year lifetime. So, it seems imminent that this technology is going to be commercialized. And, there are, in order to really meet the needs of the climate change crisis, and limit future warming to no greater than 1.5 degrees C pre-industrial levels, this technologies will need to be ramped up. And the gray line here shows the ramp up of perovskite silicon tandem cells beginning at the end of this decade. Now, though, in order to meet that demand, future materials will need to be introduced and scaled drastically, uh, such as PTAA, which we heard about in the previous presentation. This is expected to need to get expanded at an order of magnitude 12,000x current production levels. And just real briefly, background about American Perovskites. I attended a PACT workshop a year and a half ago and built a consortium, to an R&D consortium to commercialize some university technologies. We went on and our team won an American-made countdown contest. Um, I'll share some results with you of the work we're doing, and um, sort of the challenges we're hoping to solve. Uh, um, so what really we see are four main challenges with the commercialization still. First, you have the efficiency and maintaining good light absorption. Um, and even once you have efficiency, yes, there are still stability challenges with the materials. It could be photo stability. Uh, and let's say you have efficiency and stability solved. Well, then how do you scale and produce enough of these devices to meet the um, societal needs? How do you have good throughput? And then, okay, you have good throughput, but how do you also maintain economics and uh, you know consider the low cost? So those are really the four challenges that are still presented today, is that balance. And what we introduce are how we help solve these challenges is introducing a highly efficient, stable uh, alternative to PTAA, as seen here. Our Some of our materials, um, as seen in this graph, are outperforming existing materials, and uh, they're I say half of the cost of PTA, but they're actually, let me repeat, a quarter of the cost, of PTAA. And what's great is that our materials are also um, there's a patent around the materials, and they're tunable to various band gaps, as you can see here. So if you're doing a wider band gap, single junction or a double junction, or you're just doing a medium band gap, or let's say a perovskite with a low band gap, we have a variety of materials that are all highly efficient, stable. They are repeatable, so they can solve that manufacturing repeatability problem. Scalable, so we have good throughput. We help the manufacturers with their throughput, and then ultimately low cost. Again, a quarter of the cost of existing materials. So these are some of the compounds here on the right, and much of this is publicly available. But we're optimizing